Welcome. Let's talk a little bit about section 5.8. So last week you learned about sequences, specifically how to calculate recursive sequences, but there's a massive problem with recursive sequences. They are completely inefficient when you're trying to do some computational work. So if I want to, for instance, calculate something of trying to find, well, let me just give you a quick example. So and a classic example that we often look at is what are known as the Fibonacci numbers. You may have already learned about these years ago and as a kid. It's where f sub n equals f sub n minus 1 plus f sub n minus 2, where f0 equals 0 and f1 equals 1. So this sequence ends up looking like 0, 1, 1, 2, 3, 5, 8, 13, 21, where you're taking the previous two terms and you're adding it to get the next, then add and get the next, add and get the next, etc. So the next number would be 34. So we have this wonderful thing right here where we can look at. The problem with this is I've already just figured out real quickly 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This one right here is actually F9 because we started at 0, the 0 index. So this is F9. My question for you is, what is F100? And the problem with that is you would have to find the first 99 in recursive sequence to figure that out. There's actually a better strategy to do this. We preferred closed form, or those those direct form of an equation, because those formulas allow us to attack these problems. And so this is where we're going to get into a key strategy we're going to use. Your book is going to talk about this. If you look in your book, it's going to talk about just for second order. I'm going to give you a much more general, because the truth is this strategy works more. Also, if any of you take differential equations, this is something that you will apply in differential equations. All right, so let's go back to the other slides. And we're going to talk first about what is a homogeneous linear equation, because this strategy only works for homogeneous linear recursion. And then we're going to talk about the method of characteristic roots. By the way, it works for recursion, which is actually why it works for derivatives, because derivatives are recursive. Okay, so if you didn't realize that when you took calculus. Because how do you find the second derivative? You have to find the first derivative. So because that derivatives are recursive, calculus is just linear, is just discrete math with ugliness added to it. All right, so what are homogeneous linear equations? Well, a homogeneous linear equation looks like this. Now, what does that really mean? Okay, so a sub n is going to equal a constant times the previous term. This constant, for all I could care, is could be 0, it could be 0.1, it could be pi, it could be anything in the world that I want. It just has to be a constant times the previous term plus another constant times the next term, previous term, plus as far as you want. It could hypothetically go all the way back to 0. Usually they don't. I don't see many recursion things that go beyond 3 or 4, but it is completely possible, and there are ways to attack it. So when we're dealing with these situations where we have this, and we have a recursive equation to kind of work on, the reason this is homogeneous and linear, those are two things that should come up. Homogeneous means the same. So notice that every single one of these terms, so that's the things that are separated by the plus, are of the form a constant times a term, a specific term in the sequence. There is no just constant. There is no other kind of things. I don't have something where like, so let me give you, we'll give you more examples, like a sub n equals a sub n minus 1 plus n. This is problematic because n is not a term in the sequence. Therefore, it's not homogeneous. It is not of the same. Homogeneous is a really big thing throughout math. Linear. So let's talk about what linear means. Linear just means that, honestly, notice all of these are raised to the first power. We don't write the power, but it's all the first power. So that's a linear equation. I know it could have multiple variables. That's still linear. If you were to graph it, again, if any of you actually take multivariable calculus, you start getting into planes, which are essentially linear structures in multidimensional space and so forth. But the nonlinear would be if I had anything like anything squared, anything square rooted, a fraction of two terms. Those are all bad. So specifically to illustrate this idea, let's look at some examples. So here are examples of homogeneous to get ourselves started. These are all homogeneous. The first one is just simply 2 times the previous term minus 3 times the term before that. So this one, and again, all these would have to come with some prepackaged information. We have to have some initial cases. You have to have those, or else your recursion doesn't make any sense because you don't know where it started at. And that does dictate a lot of stuff. And we'll come back to that. But I'm just for the sake of, is it homogeneous and linear? You don't need that. And again, it doesn't matter if it's n or k. This is simply a variable of the index. And then you have to be consistent. So if I have k here, I'm using k again. I'm using n here, I'm using n again. Look at this one is actually called what's called a third order linear recursive equations. Third order because it goes down 3 steps. This one is called a second order because it goes down 2 steps. Believe it or not, this one, which only has 2 of them, is actually called a fourth order because in reality, this third line right there, I could have also written it, I left them off, but I could have written this as 0 times c times k minus 1 times plus 0 times c to the k minus 3. Those missing terms are really 0 times something, so we're really ignoring it. It's just going to the fourth thing. Now, the ones on the bottom are not homogeneous or linear. They fail in at least one of the categories. So this first one, notice I squared the d to the k minus 1. Because I'm squaring d sub k minus 1, it's no longer linear. It's now quadratic. That's bad. I can't use this strategy. This next line has a plus 5. That makes it, so this again, not linear. This makes it not homogeneous. And this one makes it not linear because linear, you would not have a ratio of concepts. That's now, these doesn't mean these aren't recursive equations. They're actually out there. We still often want to find their solution, the closed form. We have to use a lot of different strategies. So the strategy I'm going to talk about only works for homogeneous linear equations. I'm going to echo that again. You got to come back and watch these videos, do it, kind of just practice. You need to know what these things are. All right, so let's get to our method. It's called the method of characteristic roots. Your book wants to call it the distinct roots strategy. The general term in every book I've ever read is method of characteristic roots, except your book. So I'm just telling you, this is what it's actually formally called, because this is also the terminology that carries over into linear algebra, carries over into differential equations. It's the strategy that's talked about by most people. In fact, I'm at a conference. It's one of the things that's being talked about. It's come up. So the method of characteristic root is this. Here's how we're going to do this. I'm essentially going to look at this problem where notice I have this is a linear differential equation. Okay. And I've already stated it's true for n is bigger than 2, and I gave you the initial conditions. What I'm going to do is first look at this. If I generated a table, obviously a sub 0 is 1, a sub 1 is 1. Those are the given values. A sub 2, again, the way you find a sub 2 is this. A sub 2 would have equaled 5 times a sub 1 minus 6 times a sub 0. Well, this is 0, and this is 1, so that's equal to 5 times 1, or 5. And we can repeat this process for 19, but we would do 5 times this, 25, minus 1 times 6. That's how we get the 19. you keep doing this process and you'll notice it is growing exceptionally quick. And what I mean by that is you notice the difference. So remember in previous sequences we talked about, we had geometric and we had arithmetic. In arithmetic, you simply are adding the same amount on. Well, arithmetic, I'm adding 4, right? I'm plus 4 here. But then this one is plus 14. That's plus a lot more. Namely, that's, let's see, that would be plus 46. And we got, I'm starting to, this is now it's starting to get hard. So this last term would be a 6, and then a 4, and a 146. So notice it is growing dramatically every single time we deal with this. And there's all sorts of problems to deal with that. Like, okay, I can't deal with that. So obviously it's not adding. If it was geometric, then it'd be multiplying that by the same amount each time. So this one, which is times 5, but this one is times 19/5. And this one is times 65/19. Can you see that this is not the same number? Yet it's growing crazy fast. That tells me that one of the most likely options, not guaranteed and not set, is that it is an exponential function. So that means it is of the form something raised to a power. Yes, that looks like a geometric, but we're going to take it much more. So I'm going to make a guess that it is exponential. Exponential, again, means you have a fixed base, and the exponent is what is changing. So in an exponential function like this, if a sub n equals q to the n, and notice we're supposing q is not 0. Because if q is 0, well, then all terms are 0, and that's just plain boring, and we don't care about it. Well, if that's true, I'm going to reset, then a sub n minus 1 is equal to q to the n minus 1. Wait. To make sure you understand this, this is where students get lost. This is true because right here, I'm taking the same index and it becomes the exponent. That is all you need to understand. So a sub n minus 1 becomes q to the n minus 1. A sub n minus 2 becomes q to the n minus 2. And now what I can do is I can come back up here and say, hey, I can take my original equation and I can rewrite that now using these q a sub n and q to the n. And we get this. Well, this is now an equation that we can try to solve. So if I want to solve this, I'm going to have to literally set it equal to 0. So going back to algebra, if you are asked to solve an equation, you are trying to set something equal to 0. So notice all I did is to get to this next step is I subtracted 5 times q to the n minus 1 minus 6 times q to the n minus 2. And the reason we do that is that all the strategies to solve that you learned way back in high school were factoring, especially when you have higher dimension, is factoring, the quadratic formula. All of those are when it's equal to 0. So here I have it equal to 0. And so notice I can factor out, I want to factor out as much as I possibly can. What's the greatest common term between all these? They all have a q to the n minus 2. And if you're having trouble looking at this, you can multiply it back up. But I'll make a note real quick so you can really see. But going back to your algebra days, yes, we are using algebra, and yes, you are expected to solve basic quadratic equations. Q to the n minus 2 times q to the 2 is equal to q to the n minus 2 plus 2. Because remember, you add the exponent, same base, which happens to be q to the n. So what does that mean? That means that q to the n, I could have broken this up as q to the n minus 2 times q squared, and then I can factor a q to the n minus 2 out, and it comes out here. I do the same thing, q to the n minus 1. If I take away n minus 2 of them, there's 1 left over. And if I take q to the n minus 2 q's out of this one, well, there's no q's left, but there is the constant. And that's where we get to this point in time. So we factor this. Here's my point. I guessed because it appeared, remember, we guessed this value up here simply because it looked like it was exponential in growth. Based on that, we made a substitution. And then our substitution got us here, which gets us here. Now, a couple of things. If you have a second degree linear equation, notice this is a second degree polynomial. This is a second degree polynomial with the coefficients -5. Oh, wait, I had a +5 right here. +6, I had a -6 right here. There is that direct correlation with just second degree, but this empowers you to do way more. This strategy works for any homogeneous linear equation, not just second degree. You can do it for others because guess what? When you passed algebra, you did higher dimension as well. And if any of you say you didn't do that, well, then you didn't pass college algebra because that's one of the outcomes you were supposed to be able to do. All right, so these are we have this. Now, by our zero product rule that you learned a long time ago, that means that q to the n minus 1, the two parts, either this has to equal 0 or this has to equal 0. And that only works because they multiply together to give you 0. So again, these are basic algebraic concepts, but we're using them over and over again. So because of that, if this is equal to 0, but the only way this equals 0 is if q is 0, which is a contradiction. We've already said that q is not 0. So therefore, we can throw out that option, which all that leaves me with is when does q squared minus 5q plus 6 equal 0? Now you can solve this. Again, this is simple quadratic. You can try to factor it. They don't always factor nicely. This one does. You can complete the square. You can use the quadratic formula. All those are great. No, you do not get a graphing calculator that can do it on the exam. So if you don't know how to do that, go practice it because I will just tell you right now, it will come up on the exam. So if we solve this, we get q is equal to 2 or q is equal to 3. Those are the solutions. Again, you can factor, quadratic formula, all those will end up with q is equal to 2 and q is equal to 3. If you do that, then we can now apply. All right, hang on. So we already solved this. We said that a sub n is equal to q sub n. Let's just review all the stuff. We guessed this, and then we determined that q is equal to 2 or q is equal to 3. And so from here, we can say that it's of the form some constant a times 2 to the nth power. Because notice I'm taking the 2, I'm taking this 2 over here, and I'm putting it in for q, which that would be 2 to the n. Then I'm taking the 3 and putting it in. It's not really just going to be one of them. It very rarely is just one of them, because if it was, that would be a simple geometric. We would recognize that very quickly, not a problem. So that means it has to be some linear combination of these two solutions. But the problem is, how do I find A and B? Because we're not done yet. If we know big A and big B, then great, but we don't know them. So how do you do that? Well, it's actually, let's use what we do know. Notice we've not used our initial conditions, and they actually turn out to play an important role. So first, what happens when n is equal to 0? Let's take this formula and consider the two cases. The first case is that n is equal to 0. So a sub n is a sub 0, which we know is 0 over here. But then I plug in 0 for all the n's. So it's a times 2 to the 0 plus b times 3 to 0. And we have that right here. We just had, and again, we've now created a nice, wonderful equation. It has two unknowns, which is not great, but this is still an equation that we can work with. That's a little bit easier. Well, what about when n is 1? Well, that would give us the equation 1, because that's a sub 1, is equal to a times 2 to the first power plus b times 3 to the first power. And now all of a sudden we have two equations we've come up with. If we simplify them, they look like this right here. And I'll talk about that in just a second. This is those two equations, because any number to the 0 power is just 1. And any number to the first power is just itself. So I came up with two equations. Notice I have two equations. They are linear equations and two unknowns. If you have two equations and two unknowns, you can solve it. It's called a system of equations. Again, something you did in algebra. So again, we are using your algebra. You can solve this. There's multiple ways. That's substitution. You can do the elimination method. You can do a matrix method for any of you know linear algebra. All of those methods are fair game. I do not recommend the guess and check method. It absolutely stinks, nor do I recommend graphing, especially since you don't have a graphing calculator. So that would be problematic. So if you solve these, it turns out that A is equal to -1, B is equal to 1. The solution of this, again, if any of you want to see this, how I would solve this one actually turns out to be really easy. I can take that first equation, and that really is the same thing as writing -B is equal to A. So that means I can come to this equation. I can take that and put that in this equation and get 1 is equal to 2 times -B plus 3B. Because notice, everywhere there was an A, I can put in a -B. But this is 1 is equal to -2B plus 3B, or 1 is equal to B. Boom. And we already know that A is -B, so that means that A is equal to -1. So this was actually a really, really easy one to solve using the substitution method. Doesn't always turn out that way, but a lot of these actually do like the substitution method. So we've solved this, and we get A is equal to -1, B is equal to +1. So we can plug those back into this up here, our general formula. Big A is -1, so I could have written this real quickly again. I could have written this as A sub n equals -1 times 2 to the n plus +1 times 3 to the n, or written it this way. This one just looks a little bit cleaner because you can really adding a negative is the same thing as subtracting, et cetera, et cetera, et cetera. These are all things you should already know. So again, we're leveraging that. We're using our past concepts. And real quickly, if anyone comes back and says, I don't know that, you passed calculus to get in this class. That's prerequisite. And the prerequisite for calculus is algebra. So hence, we will reference and we will utilize all of those algebraic strategies. All right, I hope that helps. This is the strategy. Again, I'm just going to go back and run you through this, all the steps. Step 1 is we guessed, because we saw how it was growing, that it was exponential. Because of that, we then substituted in and actually were able to then turn it into this quadratic that we then had to solve by factoring out. We solved the quadratic. We found its roots, or what it could be any it'll be a polynomial of any degree. We take those roots and then we plug them in, but we still have to find the coefficients for them. So we have to use our initial conditions. And then we have to do a system of equations we have to solve. So a lot of the strategy, these problems are a little bit lengthier, and they do use a lot of your past algebra, but you can do it. Good luck. Let me know what questions you got.